Okay, we're now going to look at part 1, section 1.2, about the ionization of water and its Kw. Now, water has its own acid-base properties. Water can act as an amphoteric substance. What do we mean by amphoteric? We mean that at any one time, it can be either an acid or a base. And thus, in this reversible autoionization of water, we also call it protolysis, two water molecules interact with each other such that one of the water molecules gets protonated and it accepts a proton from another water molecule. So one of the water molecules acts as a base and the other water molecule acts as the acid. And we have an acid water will lose or donate its proton, thus it ends up becoming OH minus, that's the conjugate base of it. The other water molecule acts as a base, it will accept a proton, thus it becomes a H3O plus, which is the conjugate acid. If we now look at the pair that is interacting in this reversible reaction, and remember we always have two pairs, one of the pairs is the H3O plus with water in green, and the other pair is water with OH minus. Don't forget the acid first, followed by its basic form. This reversible reaction has an equilibrium constant. Now remember, the equilibrium constant of any reaction is the products divided by the reactants. Of course, in this case, the water here is in its aqueous form, and we put it water aqueous, and thus we're putting it in the product. Now, this Kc has a following number, so this equilibrium is something 10 to the minus 18, but actually, water in its aqueous form, almost all of this reaction exists in the form of water. And water is the solvent, of course. And here, its concentration in any reaction, in all reactions, we don't say its concentration is 0 or negligible. Actually, its concentration is so high relative to everything else that it remains essentially constant. And the concentration of water is 55 molar, 55.55. We can calculate this concentration using the equation number of moles divided by volume, and you always know that moles is mass divided by molar mass, and here we have the mass in a 1 liter solution, thus the mass is 100 grams. The molar mass is 18, and in a 1 liter solution, the volume is 1 liter, and thus the concentration of water in a 1 liter solution. Okay. This concentration is considered very high. Thus, no matter what direction, how much we go forward relative to how much we go back, essentially the concentration of water is constant. And if I treat it as a constant, I could multiply it by the Kc, take it out, multiply by Kc, and then I multiply this number by 55 squared, and we get a number called Kw. And Kw is well known to be the ion product constant of water. Okay, and its value is equal to 1 times 10 to the minus 14, or 10 to the minus 14. That is at 25 degrees Celsius, which is 298 degrees Kelvin. At any time, you could always put this equilibrium and always say that there's an equation that relates H3O plus and OH minus in a solution at any one time. By the way, this reaction doesn't go very often. So the amount of H3O plus or the amount of H plus for every single water molecule is quite small, but nonetheless, in some cases, it may become significant. Just as a reminder of all equilibrium constants, the only thing that will get the equilibrium constant to change is temperature. Everything else, I do not change an equilibrium constant with concentration. So no matter how much H plus I have in solution or how much OH minus I have in solution, my Kw remains constant at 10 to the minus 14 at 25 degrees. However, Kw can vary with temperature. And here's just a chart showing you different temperatures and the variance of Kw. Now, you don't really need to know this, but I want you to understand that it doesn't matter how much acidic my solution is. The only thing that the Kw remains constant at a certain temperature. Okay. And we're going to take it at 25 degrees. Now, one thing throughout, which is a slightly misleading, is this element of H plus. We talked about this a little bit, and that a proton never exists. It's way too small and too highly charged to ever exist in a water solution, like standing as an ion H plus surrounded by water molecules. It's not, solvated. It's actually gonna, go with one of the water molecules and become H3O plus. And every single, even water molecules, there's always interaction between this hydrogen and any other, and the oxygen, or this oxygen and the hydrogen. So water molecules are always interacting, and ions especially are always going to be in the form of H3O plus. But if you see any H plus, don't worry, it exists only in, on a piece of paper. It just means H3O plus in your head, okay? Okay, so what is the concentration of H plus? There you go, you see H plus, but and OH minus in pure water at 25 degrees. Okay? So Kw again is H3O plus, or H plus times OH minus. If this is pure water, guys, and I mean pure water, okay? Not the water that we have here, none of it is pure. Deionized and things like this, so water that has no ions in it, then the amount of H plus should equal the amount of OH minus in pure water. And so if I call this concentration X, and then this is also X, and when I solve for X, we take the square root of Kw, it becomes 1 times 10 to the minus 7. So in pure water, the concentration of H plus and the concentration of OH minus are each 10 to the minus 7. However, they're not always like this. So let's look at the variance. What is the concentration of OH minus, for example, in an HCl solution whose hydrogen ion concentration is 1.3? We're going to talk about later, slightly soon about the HCl solution, but they're already telling you that the H plus concentration is 1.3. So now, if I already have a solution and I already have the H plus, then this H plus in water, okay, this H plus, this equation, this H plus is no longer the same amount as the OH minus. And you actually have to say that the H plus is 1.3 in a solution, okay? This is the H plus coming from the HCl. Of course, we also have, remember, H plus coming from the water molecule, but we consider that, negligible relative to this 1.3. And so whenever we want to calculate OH minus okay, so in the equation, we always put whatever we have as an acid or a base, the concentration of the H plus that's already in solution and that is not coming from the water. And so the OH minus concentration will be simply divided by the H plus, and that's going to be 7.7 times 10 to the minus 15 molar. Of course, as you can see, this concentration, it's less than we would have expected in pure water. Okay? And that's because we already have some H plus, and so the autoionization, if you want, from Le Chatelier's principle, the reaction goes backward because we added some H plus to the product side, so the autoionization of water, the reaction goes backwards. Okay, just so you know, no, you're not going to get questions like these on the exam. This is considered very basic, but I like to start always from zero as if you know nothing. And so that when we build up everything, I know that you had the background information. Okay, you could just do this reading, and just always tells you that water almost never produces 10 to the minus 7 or 10 to the minus 7, especially in the presence of any. A very important remark that I want to point out is that if we have an acid or a basic solution that is sufficiently concentrated, and there's the word sufficiently concentrated. Now, what is that? We're going to discuss it quite later on. The autoionization of water can be neglected relative to any other reaction. So if I have already some acid in solution or some base in solution, I assume as if water is not doing this autoionization and as if I'm not getting any more H plus or OH minus from this water. Okay, so I assume that the autoionization of water is negligible and almost non-existent. Also, a concentration is considered negligible with respect to another one whenever it is 10 times lower. So we can usually neglect, let's say, I in a solution with respect to J if indeed I is less than 1/10 of J. Okay. And we will see this neglection concentration also a little bit later on, just pointing it out here, and I will point it out whenever it is needed